Hello, and welcome to Chapter 11, Section 1. Today we are talking about chi-square tests for goodness of fit. So out of all of the hypothesis tests that we've done, we're adding on another type. So in Chapter 11, we are focusing on chi-square, and there's three types in this chapter total. Today we do the first one, which is called goodness of fit. So to begin, let's start with this chi-square. Chi is technically a Greek letter. It's like this capital X looking thing, but it's like swirly. So fancy X squared. And then sometimes you'll see goodness of fit abbreviated as GOF because, it's too many words for us mathematicians to write out. So why not abbreviate? And especially on the AP test, if you're, running low on time, GOF would be much easier to write versus all the other letters. So when do we use this goodness of fit test? So if you think back to our other hypothesis tests that we've had like the 1 proportion, 2 proportion. What if you were trying to compare more than 2 proportions? What happens? This is it. So this goodness of fit test is for when you have multiple proportions to compare to, like some sort of claim. And so if we want to deal with more than 2 proportions at a time, you would use the goodness of fit test. All right, so let me introduce this with an example. So I don't know if you know, but starbursts are supposed to be packed with an equal proportion of each color. And in the original pack, here's my handy dandy pack, they have the pink, yellow, orange, and red. That's the original flavor. And so if they're all supposed to have an equal amount or equal proportions for each color, then if we were to test this out using like a random bag of Starburst that I bought from Target, my favorite store, obviously, then we should be able to check if this bag has at least somewhat equal proportions of each color, and then we can use that to prove or disprove their claim. So obviously we will be using a hypothesis test, so we're still doing the full phantom process. So first, before we do anything else, we're going to state our parameters and our hypotheses. Alright, so first for our parameters, because we have 4 different proportions that we're talking about, because we have a proportion for each color, then I'm just going to try to abbreviate a little bit. Here's all my different proportions, the true proportions. So I'm going to write it out as they're the true proportions of each color starburst packed into all the bags. So remember, this parameter is talking about the entire population of starbursts and all the different colors. So then writing our hypotheses, because we are comparing multiple proportions here, our null hypothesis was always when it was equal. So here the same thing, we just have to set all of our proportions equal to each other because the claim was that each of the proportions should be equal to each other. And the claim might say something like, oh, this proportion has to fit a certain percent, this proportion has to fit a certain percent, and so on. So that's kind of how you're writing out your hypotheses, your null hypothesis. It's always going to be equal to whatever the claimed percent is. So in this case, each of our proportions then should be 0.25 because we have 4 total proportions. Splitting all of our colors up should be 25% of each color. Okay. So then our alternative hypothesis, since we are testing in our null hypothesis whether all of them equal each other or all of them equal 0.25, our alternative hypothesis, we just want to see if the null hypothesis is not true. For the null hypothesis to be not true, any one of those proportions could be not 0.25, and then the alternative hypothesis would be true. So I could say something like at least one proportion is different. Because when I say is different, that just means it's not 0.25. So now that we have our hypotheses stated out, now we get to go on to name our test. This is the chi-square goodness of fit test because we have multiple proportions. And also I wanted to point out before I move on, this is the chapter where we start for our hypotheses. They're not always going to be symbols anymore. You might have to write things out in sentences and words. So sorry for the blaring bell. It's loud and scary, and this is my life. Also, I am not going to re-record that part because, no, we don't have time for that today. Okay, at this point in time, after I've named the test, I'm also going to name the level of significance that I'm going to use for my test. We weren't told what to use, so I'm just going to choose, let's go with 0.10. So not the lowest level of significance here, but still a commonly used one. All right, so our next step in the phantom process would be to check our assumptions/conditions. And they're the same as before. We have random, independence, and we usually call the last one normal. But here I'm going to start calling it large counts. And if you think back to the other test where we dealt with proportions, we always use the large counts condition anyways, where we did n times p, n times 1 minus p had to be greater than or equal to 10. Here, it's going to be slightly different. It's still called large counts, but the process to find those numbers are going to be different because we have 4 proportions here, and doing n times p, n times 1 minus p 4 times is annoying. So here is the process. Let's go through random and independence first. All right, so for randomness, we can assume this bag of Starburst is randomly chosen because when I went to Target, I kind of just grabbed one and then I got out of there. So in these crazy times, I'm not trying to stand in any store too long. Out of all the Starburst bags produced, cool. And then independence, so here, normally we check the sample size and make sure it's less than 10% of the population. So first of all, my sample size would be like how many Starbursts are in this bag, which I don't actually know. Who knows? So for right now, since I haven't even opened it yet, it's an unopened bag in case you can't see. This is new. But anyways, another way to check for independence is the packing of each Starburst bag to the next, because we're checking for independent samples. So if our sample is independent from each of the other Starburst bags, then when they packed them, it shouldn't really have affected each other. And so that's something we're assuming because obviously we don't know for sure, but we can assume this because these are assumptions. All right, last thing, large counts. So to check for large counts, we need all expected counts to be at least 5. And so earlier we talked about how large counts we used to do n times p, n times 1 minus p. So, and those had to be greater than or equal to 10. Here we're going to change things up just a little bit. Expected counts is just n times p. So take your total sample size times the proportion of that category. That number needs to be at least 5, so greater than or equal to 5. This is slightly different because we used to check both n times p and n times 1 minus p, and that had to be greater than or equal to 10. So now we're only checking n times p. We just need it to be at least 5. All right, so it's time. In order to check for my expected counts, I do need to know my sample size, so let's open this bad boy up. I feel like I'm doing one of those unboxing videos. Yeah. Okay, so let's figure out how many Starbursts they actually gave me in this bag. So many. I'm going to pause this while I count. All right, I tried to group things out. Here we go. So then it looks like I grouped them out in groups of 10. I guess I should have been more clear. So 88 total pieces. All right, so if my total sample size is 88, then for each of my proportions, I should be getting 25% of them to be pink, 25% of them should be orange, 25% of them should be red and yellow. So when I multiply that together, I end up with 22. So my expected number of orange Starbursts is 22. My expected number of pink Starbursts is 22, red, yellow, and so on. Those numbers are all greater than 5. We did it. So writing this out, because I didn't want to list all of them 4 times, I just said 22 is greater than 5 for all the colors. Cool. All right, so our next step of phantom, we get to find our test statistic. We do have a new formula for this. So our test statistic, instead of like a z-score or a t-score, is now called ChiSquare. That's the name of our ChiSquare test. So ChiSquare is like the new table or the new distribution that we need to talk about now. To find this test statistic, we are taking the sum of O minus E squared divided by E, where O stands for observed, E stands for expected. So this E number we've already found. When you take your total number of things in your sample size, multiply it by the proportion, that is your expected count. The O is the observed. So for us, because we're dealing with the different colors that we have, we are trying to observe how many starbursts of each color that we have. So in order to count all these, I have organized these by color and stacked them in tens. So it looks like for pinks, there are 34, oranges, there's 22, yellows is 16, and red is 16 as well. Alright, so I've listed my observed and my expected numbers here. I also want to go back to the test statistic formula and point out I drew my fraction line too big. So it's supposed to be the sum of all of this divided first, and then you add them up. Alright, so next what I found was each component of my chi-square statistic. So each component just means I'm just plugging in each of my observed values into the formula, my observed and expected values into the formula for the chi-square test statistic, because at the end I have to add all of these up. That's what the sigma symbol is for. So you're adding everything up after you've done the O minus E squared divided by E. So these are each of the components that I got. When I add them together, I end up with 9.8182. So that's my test statistic. This is my chi-square test statistic. So obviously this was a process. I wrote everything out because I am a great teacher and I show all my work. However, obviously we are doing everything on the calculator because we got this. That's what our graphing calculator is for. So in the calculator, the easiest way to do this is to put all of your observed values in L1 as a list and all of your expected values into L2 as a list. So here I have L1 are all my observed values, L2 are all my expected values. To calculate each of these components quickly, I can do that in L3. So if you scroll all the way up to the top, you can type in O minus E divided by E, except instead of O and E, we're using L1 and L2. So I'm going to start my parentheses. O is in L1, so I'll type in L1, minus E, so that's L2, and I'm squaring that, dividing by E, which is L2. So when I type it in just like that, as long as L3 is highlighted, it'll calculate each of these numbers for me, and there's each of my components. So adding them up, you can use the sum function in the calculator. So let me get out of this screen. So second mode to get back into my home screen. If I do second stat and then go over to math, number 5 is sum. I can sum L3 for myself, and that'll give me that entire list of numbers added together. However, still, there's even a faster way to do this, but we'll get into that in just a moment. So now that we have our test statistic, we can move on to our next step of finding the odds or the probability. Before we do that, I wanted to show you the chi-square distribution table. Because this is a new distribution, I also wanted you to see the formula itself. So hopefully you recognize that when you apply this formula for the test statistic, every single time your numbers are always going to be positive. So when we looked at the z-scores and t-scores, those two distributions, you were allowed to have both negative and positive numbers. The chi-square distribution only has positive numbers because of the way the formula is. We're squaring something, so you always end up with positive. So here is part of the table. I only copy pasted part of it. So this is the one you'll see on the formula sheet of the AP exam. This is the chi-square distribution. So this is another one where, depending on the degrees of freedom, the shape of the distribution will change. So as you can see, it starts out skewed, and that's when your degrees of freedom is lower. So as you get higher in your degrees of freedom, this shape of the curve gets closer and closer to that normal shape again. So reading this table, at the top you'll see the tail probabilities, and then everything in the middle are actually the test statistics. So the way to use it is to figure out your degrees of freedom and then match your test statistic that you calculated to be as close to the one in here as possible. The degrees of freedom formula is to find the number of categories that you have, subtract by 1, not your sample size. Because our sample size was 88 here because I had 88 starbursts total, but that's not what we're calculating for. So our categories are our different colors. So we had 4 categories minus 1 would be 3. So our degrees of freedom is 3. So when I look down at this table now, I'm going to use the degree of freedom of 3 row, that's right here, and my test statistic was 9.8182. So I'm going to go down the entire row here and look for the one that's closest to 9.8182. So it looks like it would be right in between this 9.35 and 9.84. So this tells me, because my number is right in between these two numbers, that the tail probability that it corresponds with is the 0.025 and 0.02. So this table does not tell me the exact p-value. It only tells me what my p-value is in between, but this is still enough information to actually compare it with alpha. Remember earlier we said alpha was going to be 0.10. So we are comparing these numbers. If our p-value is in between these two numbers, it's got to be less than 0.10, which means if my p-value is less than my level of significance, we would reject HO. All right, so obviously this table is a little bit cumbersome. We talked about the graphing calculator earlier and how there is another shortcut, so let's do that now. So with my graphing calculator, if you go into Stat over to Tests, I just scroll straight up because it's towards the end of the list, so it'll loop back around. You're looking for the ChiSquare GOF test. GOF for goodness of fit. One small detail here is if you have the TI-83 calculator, it does not have this function. So sorry, no shortcut for you. But if you have anything beyond that, you have this function. So let's hit enter. So here, this is where you want to put your lists. We put all our observed values in L1, expected values in L2, and then our degrees of freedom here was 3, so we can just have our calculator calculate everything. So it automatically gives us our test statistic. We don't even have to calculate it ourselves. As long as you type in your L1, L2, it'll do it for you. It calculates your p-value so that it's actually an exact number for the probability. We get 0.0201, which also matches what we got from the table, just more exact. Degrees of freedom, they restate it for you. And then here, these are all your components. So that was when we calculated all our components of chi-square earlier. It'll also list that out for you. If you scroll to the right, it'll give you all the components. It's hard to read because we have so many decimals, but it's there. Okay. All right, so now we get to make our conclusion. So it's the same conclusion as before. Our p-value of 0.0202 is less than our alpha value of 0.10, so we reject HO. There is convincing evidence that at least one proportion of starburst colors differs from 25%. So remember, this last part of the conclusion is just your HA in words. All right. So one other thing that I want to mention here then, because we're saying that at least one proportion of starburst colors differs from 25%, now we want to know which color was it? Which color is the one that threw off the pattern? Well, first of all, if you remember our observed values, we were saying they were all supposed to be about 22. Orange was the only one that met that. There were a lot of pinks and not very many yellow or reds. But here, just looking at our numbers, it looks like 34 would have been like the furthest away from what we expected. And that's basically what we're looking for here with our components. So if you look at your components, the number that is the biggest, so with the pinks, this just shows how far off from your expected value you are. So the number with the biggest component is what would have affected the test statistic the most. And so if it affects the test statistic, it's going to affect our p-value. So whatever component is biggest, that's what's going to have affected your test the most. So whenever you reject HO, you want to add this into your conclusion. Look for your biggest component of the chi-square number, and then add in particular, the proportion of, and then whichever category this highest component referred to. So for us, it was pink starburst, was greater or less than expected. So if it's less than expected, like whatever number that you got, then you would choose less. For us, it was greater than expected because we got a lot of pinks. And so this just points out to people, this is what affected my hypothesis test. If you had failed to reject, then we would have said that there isn't a proportion that was different. So there would be no, in particular, anything that was out of the ordinary because we weren't able to prove that at least one proportion of starburst colors differs from the 25%. So you only have to do this when you reject HO. Okay, that's it. Thanks for dealing with all the bells happening today. They just occurred at bad times. But anyways, don't forget to like and subscribe. Thanks for watching. See you next time. Bye.